Hello, everyone. So let's get started with one of the first sessions. There are two sessions in parallel. This is rendering one, so there will be a second rendering session tomorrow. As you realize, we have delayed the schedule by 15 minutes, so no worries. Each talk will have the original allotted amount of time. There are 6 talks, 15 minutes each, so that will be a total of 90 minutes. Hybrid format, so we have 3 of the 6 talks be delivered remotely through recorded videos. We hope to have some of the authors available for live Q&A after their talk. And also 3 of the talks are in person. And I have already made contact with the 3 speakers who are here, and will make it feel like a usual conference. So without further delay, let's go ahead and start with the first talk, which is an online talk. And the title of the talk is PanoSynth VR Toward Lightweight 360-degree Video Synthesis from a Single Panoramic Input. And it is an ISMAR conference paper. And the authors are John Weidhofer, Richard Gill, Anthony Dixon, Stephanie Zollman, and Jonathan Ventura.
Hello, everyone. I'm John Weidhofer. I am a master's student at California Polytechnic State University in San Luis Obispo, California. And today I'm presenting PanoSynth VR. 2D panoramas currently allow users to experience an immersive 360-degree environment as long as they remain at the focal point at which the image was taken. This is great for desktop viewing. But when we add in other mediums like VR, the paradigm changes slightly, because users can translate. Hello, everyone. I'm John Weidhofer. I am a master's student at California Polytechnic State University in San Luis Obispo, California. And today I'm presenting PanoSynth VR. 2D panoramas currently allow users to experience an immersive 360-degree environment as long as they remain at the focal point at which the image was taken. This is great for desktop viewing. But when we add in other mediums like VR, the paradigm changes slightly, because users can translate around the scene. As the users approach the wall of the panorama, things start to appear fake, because there's no motion parallax with distant objects. Researchers have come up with several innovative solutions that preserve the illusion of the 3-dimensionality and depth as the user moves. One of these approaches is the textured depth mesh. Textured depth meshes map a panoramic image onto a mesh created from the depth map of the scene. This results in a 3D environment with sharp resolution, but the quality of the result is highly dependent on the quality of the depth map. If the depth map is low quality and there are smooth objects in the scene, these objects can appear more jagged than they would in real life. Another approach is the multiplane image. Multiplane images convert a single image into a series of semi-transparent layers. Pixels from the original image are assigned to a plane with an alpha value based on the probability of the object existing at that depth. When the user moves around the scene, the planes parallax and alpha blend, creating the illusion of depth. This produces convincing imagery, but the original implementation didn't take panoramic content into account. PanoSynth VR extends the multiplane image paradigm to panoramic images. It takes in a cylindrical panoramic image and produces an environment with motion parallax and the illusion of depth, using a system called multi-cylinder images. This system can work with photos captured on consumer user devices like cell phones, and it has a fast inference time, around 383 milliseconds. And all of this creates an immersive VR viewing environment. Here's an example of our system at work. We added a sinusoidal wobble to show the parallax effect. In addition to the main system, we created a synthetic data pipeline for our evaluation process. We found another way to compute the scaling factor, and we dealt with issues in the panorama using wrap padding. Finally, we created a user study to test this out with real people. Here's the system overview of PanoSynth VR. It accepts a cylindrical panorama, which is then passed through a convolutional neural network. This network outputs 32 multiplane panoramas. We map these multiplane panoramas to 32 concentric cylinders, and we render the result from the inside of the innermost cylinder. Our system also can predict disparity. And you could see this by mapping the alpha values to colors. The first issue we came across was wrap padding. You could see in the top right that the panorama has a disagreement with disparity on the right and on the left of the image. This is because we don't have clarity that this image wraps around when we're performing the convolutions. To fix this, we padded the side of each image by taking the left half of the image and appending it to the right half of the image and appending it to the left. When we pass it through the convolutional neural network now and take off the padding, the disparity matches between the sides. With the system working as expected, we created an evaluation pipeline. We use the Habitat Sim package to load data from the data sets of Replica, Habitat Matterport 3D, and Gibson. We use the floor plans in these data sets to choose locations far away from the walls and took central panoramas. We then found random scene coordinate offsets from those panoramas and took snapshot images from different perspectives. We passed the original panorama to the PanoSynth VR system and rendered it out in our MCI renderer, and then used those same scene coordinates to take the same snapshots within the MCI renderer. We compared the predicted snapshots with the ground truth to see how well the scene matched the original. Another issue we had with evaluation was the scaling factor. While the convolutional neural network implicitly predicts the scaling factor, it doesn't predict the absolute scaling factor of the scenes, only the relative scaling factor between objects. Tucker et al. Solved this with multiplane images by using the mean. Specifically the mean difference between the disparity and the point set. We found this to be drawn to outliers when the rendering wasn't perfect in the ground truth. So in our case, we used the median, and we found it to be much more robust against these outliers. We tested PanoSynth VR MCI renderer against the depth mesh renderer on 700 synthetically generated snapshots from 26 scenes. Our model outperforms the mesh renderer in SSIM and PSNR metrics, but the mesh renderer outperforms in perceptual metrics of LPIPs and MIFD. Since we had this disagreement between these two sets of metrics, we also decided to conduct a user study. We tested 4 hypotheses in this user study. In the first, we found that users were felt a higher significant presence when they used the PanoSynth VR MCI renderer compared to the mesh renderer. And while we found that more users generally had a higher sense of depth perception in the MCI renderer, we did not find a statistically significant number of them did, and so we rejected this hypothesis. For overall visual quality, we had the users rated on visual quality and the number of artifacts in the scene. And we found that the MCI had statistically significant higher overall visual quality and statistically significant lower overall artifacts. And finally, when we asked the user's overall preference between the MCI PanoSynth VR renderer and the mesh depth renderer, 88% of them preferred PanoSynth VR. In conclusion, PanoSynth VR provides free viewport view synthesis from a single cylindrical panorama that can be taken with consumer cell phones. It provides real-time inference, which lowers the barrier to use, and it performed the highest on SSIM and PSNR metrics. When we conducted a user study, PanoSynth VR was the overwhelming favorite for users.
Thank you. Glad to see that we have the authors standing by for answering your questions. So any question from the audience, we do have a mic that you can get if you want to ask a question. The questions coming in from online are going to relate to us, I believe, from somebody at the back. So let me start while we're trying to figure out more questions. What is the translation range of the viewpoint that you're catering to? Is it just the interpupillary distance of a few centimeters between the left and right eyes of the viewer, or is it, more significant translation? So that's my question.
We tested at 10 centimeters and 50 centimeters away from the center of the original panorama. And so we can actually you can move your head a little bit back and forth and get the scene from several angles. If you go any further than that, you actually end up, the scene ends up blurring and it ends up being a little bit, it ends up being unrealistic, you could say.
Thank you. Any questions from the audience? Please stand up, wave your hands. Yes, we have a question there.
Hi, thanks for the talk. So there was this disagreement between the perceptual metrics and SSIM and PSNR here. And typically we end up using the perceptual metrics because it works, correlates better with user studies. Is it that these metrics didn't well because you're considering panoramic images, or can you elaborate why you think the user study correlated better with the SSIM and PSNR in this case?
Yeah, so we found in the user study that people were put off by the depth mesh renderer when there were artifacts in the scene. In terms of the perceptual metrics, the depth mesh renderer did a little bit better because it was basically picking up on the sharpness of the image. And so it looked closer to reality as you approached the edges of the panorama, while PanoSynth VR tends to have a blurring effect due to how the alpha blending works as each layer parallaxes. And so to answer your question, I think the perceptual metrics work better with the mesh depth renderer, but it didn't take into account the stretching of the textures, and that's what we picked up on in the user study from user feedback.
Thank you. There is another question somebody's trying to ask there in the corner. Can you get them? So while you're getting the mic there, well, that's fine. Okay. So we have one more question from the audience.
So hi, thank you for the nice talk. I'm Katie from Hamburg University. What my question is, you mentioned about the frame time is around 300 milliseconds. Did you measure the motion sickness, the perceived motion sickness from the user, and how do they perceive this large latency?
So the 383 milliseconds is the inference from the single panoramic input to the 32 multiplane panoramas. When we render this, we could actually render it at 30 to 40 frames per second in a web renderer. And at that point, that's a limitation of the rendering medium. If we had it, we haven't tried this, but if we had something in Unreal, perhaps we might be able to get higher frame rates, because at that point, it's a limitation of the renderer, not necessarily the model. So we haven't necessarily tried something like that, but the 383 is with reference to the model inference and not the live experience.
Thank you very much. Let's thank our speakers again. Let's move on to the next talk. Thank you. So our next talk is in person, a local talk. So the title of the paper is Temporal View Synthesis of Dynamic Scenes through 3D Object Motion Estimation with Multiplane Images. This is also an ISMAR conference paper. What I really mean by that is that it is the conference track. I will let you know when we will get to IEEE TVCG papers and so on. So the authors are Nagabhushan Somraj. He'll be giving the talk. He's getting set up. As well as Pranali Sanchetti and Rajiv Sundararajan.
Hello everyone, sorry for the delay. So I am Nagabhushan Somraj, and I'll be presenting our work on temporal view synthesis of dynamic scenes through 3D object motion estimation with multiplane images. First, let's try to understand the problem of temporal view synthesis. Consider this scenario where a user is playing a game or exploring a virtual environment on a head-mounted display. In this scenario, as the user moves through the scene, the graphics renderer would update the frame based on user's motion and the weaving direction. However, on low compute devices, the graphics renderer may not be able to keep up with user motion. This can lead to frame drops or lagging, which can cause user discomfort. One solution to such problems is what is known as interleaved reprojection, where we ask the graphics renderer to render alternate frames, as seen here, probably the frames that are shown by red arrows. And then we can use a prediction engine to quickly predict the intermediate frames based on the updated user pose. So the temporal view synthesis, the goal is to predict future frames using past RGBD frames and the relative camera pose. Although we motivated this problem in the context of VR applications, it is also applicable in first-person PC games and so on. One can study temporal view synthesis in two different settings. In the case of static scenes, as shown in the top video there, only the user is moving through the scene. In such scenarios, most of the future frames can be generated by reprojection, and the main challenge lies in infilling the regions disoccluded due to camera motion. However, in dynamic scenes, as shown in the below video, the objects in the scenario will also be in motion. Like as we see here, there are two cars in the scene, which are also in motion, while the user is probably moving into the scene. In this scenario, although the camera motion is known, the motion of objects will be unknown and needs to be predicted. This is the main challenge in the temporal view synthesis of dynamic scenes and is the focus of our work. Now that we understand the temporal view synthesis, let us look at a couple of related areas of research, namely novel view synthesis and video prediction. Dr. Henry talked today morning about novel view synthesis, where the goal is to generate some images of a scene from novel viewpoints, given images from different viewpoints. The recent works in novel view synthesis use volumetric representations such as multiplane images that John talked in the previous talk, and also neural radiance fields, which have been a buzzword recently. However, these models do not model any object motion in the scenes. Recently, the work by Lee and others extend novel view synthesis to dynamic scenes, but they do not focus on predicting future frames. The other related work, video prediction, is much more closer to temporal view synthesis, where the goal is to predict future frames using past frames. So recent work on video prediction can be classified into two buckets. One set of approaches use sequential models such as RNNs or LSTMs to capture the entire past in a latent representation from which future frames are predicted. The other set of approaches model motion explicitly in terms of optical flow and predict future frames by predicting future optical flow. However, neither of these approaches take into account the known camera motion, and hence the performance may be suboptimal. Thus, temporal view synthesis sits at the intersection of both novel view synthesis and video prediction. Our work can also be thought of as incorporating camera motion in these flow-based video prediction models. Our approach to this is to decompose the overall motion into object motion and camera motion, or the user motion. For example, we see the same video here. Instead of predicting the entire next frame or the motion for the entire next frame in a single shot, we do this in two stages. In the first stage, we assume that the user or camera is static and only predict the object motion. Then we freeze the object motion and account for the camera motion using the known relative pose. We also visualize the optical flow corresponding to the videos below them. We observe that the optical flow due to camera motion is more dominating, whereas the optical flow due to object motion is more localized. This decomposition of the motion into object and camera motion also helps our model to predict the object motion more accurately. One approach to predict the object motion would be to estimate the object motion in past frames and then extend it or extrapolate it. However, the motion in the past frames is a mix of both camera and object motion. Thus, we first need to isolate the object motion in the past frames, and then we can estimate it. So our solution here is to warp all the past frames to the same camera view, and then feed it to an optical flow estimation algorithm. which gives the flow corresponding to the object motion. We then extrapolate this to obtain future object motion, and then add camera motion to it and infill the regions, infill any disocclusions that can occur to get the future predicted frame. However, if we use an off-the-shelf optical flow algorithm, we find some distortions in the predicted frame. For example, in the image, in the video shown here, the left image corresponds to one frame of a video. The middle video shows what we expect the motion to be, and the right video shows what exactly happens when we use an off-the-shelf model. We observe that as the car moves towards the left, some part of the building, which should actually be static, also moves with the car. This is because optical flow is usually incorrect in occluded regions, and as a result, the predicted frame can lead to more distortions. Why is optical flow incorrect in occluded regions? Because it does not have corresponding matching points in the previous frames. Our approach here is to use a more structured way of estimating optical flow. We use a representation called as multiplane images. We'll see a little bit more about it in the next slide. So when we use a 3D representation and estimate optical flow between them, what happens is that the moving foreground object and the relative background get separated, and as a result, this helps our model to estimate more accurate optical flow. So let us look at a bit in detail about these multiplane images. So multiplane images splits a given RGB frame into multiple planes placed at different depths in the scene. So every pixel in a frame will be assigned to one of these planes or depth planes that are there. Although in the previous talk, John talked about alpha compositing. In this work, because we know the ground truth depth, we can assign each pixel to a single plane without the use of multiple alpha values. What this does is that, in the example that we saw earlier, the moving car and the static background get separated onto two different planes. As a result, when we estimate the optical flow for the occluded background region, it only depends on its neighborhood in the background and not on the car. However, there are a couple of challenges when estimating optical flow with multiplane images. The first challenge is that multiplane images are inherently sparse. Optical flow typically involves finding correspondences between the two sets of images or MPIs, and these empty regions in MPIs can cause incorrect correspondences, leading to incorrect estimation of optical flow. We solve this by designing a masked correlation layers and use partial convolution layers when estimating the optical flow. Further, the objects can move across different planes in an MPI, and because the MPI uses discrete depth planes, we model the motion as a probability distribution. Moving on to evaluation, due to the lack of any large-scale data sets that are available to evaluate temporal view synthesis models, we develop a new database using Blender. Our dataset consists of 800 videos of diverse scenes. Each video is at full HD resolution. Our videos contain both indoor and outdoor environments, and we also have some fancy objects like Batmobile and Millennium Falcon, and so on. I think the first two videos also have Wingardium Leviosa as well. Along with the RGB frames, we also provide the ground truth depth and the camera pose. We'll now look at the predictions of our model when predicting a single frame into the future. So as shown at the top, the green frames correspond to the frames rendered by a graphics renderer, and the red frames are the frames predicted using our model. So the top left video corresponds to the frames only generated by the graphics renderer, and we can see that the video is slightly discontinuous. However, on inserting the frames predicted from our model, the video becomes much more smoother. The incorrect predictions by DPG model can lead to distortions and appear as temporal flicker artifacts. We'll also look at a more challenging case where we ask the model to predict 4 frames into the future using the past frames. In this scenario, we can see that the input video is much more discontinuous, but upon inserting the frames predicted by our model, the video becomes much smoother. For quantitative evaluation, we use our dataset and MPI's Intel dataset, which is a smaller one and is mainly designed for evaluating the evaluating optical flow estimation models. So we evaluate our models on two levels. One at the frame level by evaluating each of the frames predicted by the models using image quality assessment measures such as PSNR and structural similarity. We also evaluate the video predictions at the video level using a ST-RED metric, which evaluates both the spatial and temporal quality of the videos. In the plot shown here, the left one corresponds to PSNR metric. For PSNR, the higher value denotes a better quality. The blue lines correspond to the performance on our data set, and the orange lines correspond to the performance of different models on the MPI Intel data set. We show the performance of our model with the red dotted boundary. We observe that our model is able to outperform all the existing models in terms of PSNR, and the trend continues to be the same for structural similarity as well as ST-RED. Note that for ST-RED, lower value denotes better quality. We also observe that in general, the performance on Intel is slightly lower than the performance on our dataset for all the models. This is because Intel dataset is primarily designed to be challenging for flow estimation, which makes it much more challenging for prediction of future frames. Recall that I previously showed a failure case of an existing optical flow models. So we observed that as the car moves towards the left, some part of the building was also moving with the car. Here we will see what happens when we use MPI in estimating the optical flow. We observe that here there are no distortions in the building, that is, and the background building remains as it is, and the predicted optical flow or the estimated optical flow is also much more sharper. We find that the average endpoint error in flow estimation decreases by a whopping 38% when we use multiplane images for estimating the optical flow. To conclude my talk, we developed a framework for predicting future frames based on the past frames and the relative camera pose. We did this by decomposing the overall motion into camera motion and object motion, where we estimated the object motion using multiplane images in 3D. We also developed a new database of 800 videos, and we showed that our models achieve state-of-the-art performance. We are currently working on extending this work to natural videos where the depth may not be available. Also, one can simply use an off-the-shelf depth estimation algorithms to get depth map and then apply our current framework. There has been some work on estimating multiplane images directly from images, and which appears to be promising. So such a kind of model would also be useful in the remote presence or telepresence applications that Dr. Henry talked in today's talk. Thank you.
Thank you. So we have time for one question. One question from the audience or online. Okay. Yes, there is a question at the back. Yeah, you'll do it. Okay, thank you.
Yeah, hi. Thank you for the nice talk. So I had a specific question with respect to your approach of using this object motion model. So you mentioned that you use a linear interpolation approach. And my question was, does it really work when the object actually makes a turn, maybe a left turn, a right turn, or when it is not in a linear path? And how do you deal with this?
Yes, that's an interesting question. So in this work, we do not focus on actual prediction of such complex trajectories. And usually at high frame rates that we consider, we observe that it does not cause a lot of distortions. However, in such scenarios, one can use any existing models. There is a lot of work on how to predict future frames. We can use any of such models or augment them in our framework to account for such complex motions.
Thank you.
Thank you again. Thank you.
Thank you.
So our next talk is also a in-person talk.
Hello everyone, I'm Sachit from the Augmented Human Lab from the University of Auckland, and here I am to present XRT at ISMAR 2022. So in order to improve the immersion and realism in the XR applications, many researchers have recognized the importance of rendered feedback. And for example, combining multimodal feedback modalities such as tactile, smell, or taste could create more realistic virtual experiences. However, haptics relating to users' clothing is still largely underexplored in the XR community. And this seems a missed opportunity, as it is through the clothing that users often feel the environment regularly. For example, the cloth deformation could happen due to external forces or due to body configurations or direct contact with external objects. And therefore, in our research, we aim to enable XR developers to render the effects of virtual environments on real-world clothing in an easy and rapid way. So in this work, we introduced XRTIC, a prototyping toolkit that enables XR developers to introduce the feedback of cloth deformations into XR applications. And XRTIC is a fully functional implementation that comprises of modular plug-and-play cloth actuators and a controller bus system and a controller interface. And here are the three main contributions we make through this project. And the first one is the system requirements gathered in several interviews with XR developers regarding the development of the toolkit. And these requirements reflect the methods and challenges of adapting fabrication techniques for shape-changing interfaces in VR context. And the development of a prototyping toolkit is the artifact contribution we make in this project. And this artifact comprises of modular cloth actuators and a controller interface. And this control interface can map the cloth actuators with the XR applications and control them in sync with the VR content. And the third key contribution we make through this project is the findings gathered from a user study with several XR developers. And we explored how does XRTIC support adding cloth deformations with XR applications and how it supports creative exploration and what are the challenges they encounter when using the toolkit. And let me tell you a bit about the actuation principle of XRTIC actuators. And we extend our prior work, cloth tiles, which was presented in CAI 2021, to develop an actuator band with 4 different cloth actuators. And this is a diagram of a basic XRTIC actuator. And the node part of the actuator was 3D printed using solid 3D printing filaments, and the flexible base layer was 3D printed using flexible 3D printing filaments. And to tell you a bit about the dimensions, the thickness of the flexible base layer is 1 millimeter, and the thickness of the solid PLA node is about 3 millimeters. And we used the shape memory alloy wire, in other words, an SMA wire, to power up the actuator to generate some internal forces inside it. And the SMA wire was mounted through the hole in the 3D printed node part. And male header pins were soldered at the end of the SMA wire to retain the easy plug-and-play behavior. And we used snap fasteners attached to the back of the XRTIC actuators to create an easy attachment mechanism with the clothing. And when the current is applied, the SMA wire shrinks. In other words, it gets shortened. And it generates an internal force in the 3D printed substrate. So likewise, we utilize these forces to deform the clothes in certain motions. And here are the 4 different types of actuators we included in the XRTIC actuator bank. And let me tell you a bit about each of them separately. And the tapper can deform the clothing towards or outside the body in a specific clothing area. And it pushes the clothing towards the flexible base layer to create a pointy shape. And the puller can pull or push the clothing from the edges of the clothing. Like when activated, it drags the border of the clothing from the attach point away from the flexible base layer. And folder can fold the clothes along a straight line, and it folds the clothing across the flexible base layer when the current is applied. And the compressor actuator can render compressions on clothing, especially around limbs like body areas. And it squeezes around the applied body area when activated. And here is a short video clip that shows how these actuators work. And this is the tapper. This is how the puller works. And this is the folder. And this is the compressor. And we developed custom-made PCB nodes that can be connected in a bus architecture to control these actuators. And each node can simultaneously control 4 actuators, and all the nodes can be connected to the controller unit via I2C protocol. And the control is connected to a 9-volt power supply, and depending on the required power for each actuator, we control the duty cycle of it. And we used Unity C# scripts to control the actuators with the XR content, and the developers only had to import the serial port class from the library to enable USB communication with the actuators. And these actuators are activated by sending a comma-separated string to the control unit. And the parameters were the activation duration, the ID of the PCB node, and ID of the channel, and the actuator type. And we analyzed the actuation behavior of exotic actuators in different conditions, and we placed the camera in the same plane as the actuator, and we recorded the actuation behavior of it, and we tracked the actuation angle in each condition. And this is the behavior of the measured actuated angle concerning activation pulse duration, which was varied from 500 to 5,000 milliseconds. As you can see here, the cool down time takes approximately the same time, regardless of the activation time. To analyze the frequency of deformations, we measured the activation angle with a constant 1,000 milliseconds activation duration and a variable cool down time. As you can see here, when cool down time is getting less, the actuators tend not to go to its neutral state. Based on these, the conceivable frequency of actuation should be considered when interfacing the actuators with the virtual content. And we also explored the effect of different fabric types on actuated angle, and the red color line indicates the baseline actuator behavior when the actuator is not attached to a clothing. And when the thickness or hardness of the fabric is higher, the range of the actuations get reduced. And therefore, when installing the actuators, it is essential to consider the properties of the fabrics to achieve an accurate deformation. And to observe how users find XRT, we performed a user evaluation with a set of XR developers, and the experiment consists of 2 sessions. In the first session was about a familiarization session with where participants got hands-on experience with XRT, and they in the second session they did an open-ended exploration of application development using the XRT toolkit. And each participant successfully implemented a practical XR application with XRT, and the users came up with diverse application scenarios, like simulating the presence of an object or a person was one common theme we could identify among those applications, and the virtual handshake enabler was one example for it. Another interesting type of an application was using XRT to enable different notification on the users, and the directional queue provider was one example for it. And additionally, some participants developed more serious application scenarios. For example, a participant developed an arm sleeve with XRT actuators to simulate the impaired limbs of a stroke survivor during rehabilitation processes. And with all those findings, we found that our toolkit was easy to use for XR developers and supports iterative prototyping to enable cloud deformations in sync with XR applications. And in addition, we also developed 3 example use case scenarios that XRT can enhance the XR experiences. In the body perception alternator, the virtual abdomen area would expand when the user eats food. Then simultaneously, we control the compression levels of the user's shirts to simulate these tight clothing. In the ambience controller, individually controllable holes on the clothing open up depending on the wind in the virtual forest. In the microtactile renderer, we simulated the sense of a bird standing on a user's forearm. As XRTIC is one of the earliest explorations of incorporating cloth actuations in the XR domain, we believe there could be several future opportunities related to this project. And I would like to highlight a few of them here. And from some of the findings of the user evaluation, we learned that an API could actively provide guidance and warnings to developers during the development processes. For example, the insights about minimum distances between the cloth actuators or suggestions on ideal body locations for different actuators could be an insightful information to the users. And providing haptic feedback is one potential application of the XRTIC toolkit, and evaluating these haptics effect on of different actuators on different body areas could be another exciting research gap that could be investigated in the future. And with the latest technologies associated with cloth simulations, and an extended version of XRTIC could have ways of previewing these cloth actuations in a digital platform, and this will allow developers to iteratively program the desired cloth deformations in virtual setup before deploying the cloth actuators in the real world. So in conclusion, we believe XRTIC will provide a strong commencement for the XR community to use cloth deformation in novel ways with XR applications. And here's my amazing team behind this project, and we are looking forward for future collaborations related to this project and other projects. And you can also check out our websites for more details. And so feel free to contact us for further discussions. And this is the end of my presentation, and I hope you enjoyed it. Thank you.
Thank you very much. Thank you. Thank you very much. Very interesting. Questions from the audience? Yes. So we have a question right here. Thank you.
Yeah, very interesting talk. I wasn't sure what the rendering part was, but like from a haptic contribution to XR, I think it's very interesting. So one of my biggest question, I mean, I have multiple, but the thing so it seems like a very Boolean operation, right? Like you pass current, it contracts or whatever, like the length of the wire contracts, and you stop the current, it just immediately falls. Like the fall is pretty sharp, right? Can you control it to a little bit more continuous domain rather than just like so that, you can actually possibly simulate different cloth dynamics as opposed to maybe very,
Yeah, interesting question. I mean, in the first contribution, we found that we interviewed several XR developers to get this insightful information about the cloth actuation. And of course, we can control the cloth deformation in a more continuous way, not like a Boolean operation. Like since we are controlling the PWM signal, we can control the intensity of the actuation, of course. And the one thing we noticed that the XR developers didn't like using to play with the numbers. Like, for example, if the range is 0 to 255, so the XR developer could enter a number between these two values, and the PWM signal would drop by that amount. So instead of letting them control the actuators in the whole range, we put several levels where they can play with the actuators. Like, for example, from 0 to the maximum level, we only let the XR developers to control, as you mentioned, like a Boolean operations, like 0 to 1. So, of course, we can control them in that range whenever we want, like how much we want and stuff. So there is no limitation controlling the cloth actuators in that way. So it's just the two.
Your images showed very Boolean squares. I was
Oh yeah,
sure
so
what.
For this part of the toolkit, we did that. Maybe in the future, we can let the XR developers the freedom to feel the freedom of using.
So the length is directly correlated to the current you pass, is that?
Yeah, exactly.
Okay.
Yeah.
Thank you. One more quick question. Bruce?
Thank you very much. The devices seem to be you attach them, and if you're going to wash your clothes, you remove them from the clothing. Have you considered what it's going to take to actually have them permanently embedded in the clothing so you can actually put them in the washing machine?
Yeah, the thing is, actually, we made them plug and play because they wanted to use the XR developers can use them on different clothing and it wouldn't harm the clothing. And there are so many factors beneath that exploration. And the thing is, I haven't like explored the durability of these actuators with by, as you mentioned, like by embedding them in permanent way. So yeah, in another project we like embedded the cloth actuators permanently, and so far, I mean, now it's been 1 or 2 years, and still they are on the clothing, but I haven't washed them yet.
Thank you. So 2 years is about as long as you might want to go. Thank you.
Yeah.
So thank you very much. We're moving on to the next talk. We're a little bit short on time. Thank you. So the next talk is a TVCG invited paper, meaning that it was first submitted to TVCG, and then once it was accepted, the authors have decided together with TVCG that this would be an appropriate venue for presentation. So the title is Good Keyframes to InPaint, and the authors are Shohei Mori, Dieter Schmalstieg, and Dennis Kalkofen. So it is an online talk.
Hello everyone, I'm Shohei Mori at Graz University of Technology. Today I'm presenting our work, Good Keyframes to InPaint. Diminished reality is a conceptual counterpart of augmented reality. In other words, augmented reality adds more information to the user's perceived environment, but diminished reality deletes or reduces some part of the environment. To this end, diminished reality systems require reconstructing an occluded background to substitute it into the current view to cover the occluding object. Thus, the occluding object becomes invisible in our vision. Depending on available resources, we can categorize the methods into 2 types. One uses multi-view images and the other uses an inpainting technique. Our aim is related to the inpainting diminished reality system. Inpainting here refers to a process to collect pixels from the surrounding area of a region of interest to hide the region of interest with plausible pixel clusters, which is also known as exemplar-based image inpainting. Inpainting diminished reality systems often use a keyframe so that a single inpainted frame is reused in the subsequent frames. Keyframe inpainting helps keep coherent inpainted results over time or keep interactivity by updating inpainting results while showing the incomplete but ongoing inpainting process. If the keyframe inpainting results in good quality, then the system can guarantee the quality of the later frames. But if not, it keeps failing. Therefore, the user needs to select the keyframe carefully, but the question is how? Now we have multiple frames here, but can you tell which will inpaint the stuffed bear the best? Let's pick up 3 frames for brevity. In reality, the problem becomes a bit harder when it comes to a 3D scene inpainting. A system needs to inpaint both in color and depth domains. However, background reconstruction is often hidden from the user when the main application runs in color space. This is why we want a metric that suggests which frame to select as a keyframe before running the inpainting. So far, the best solution is trial and error, unfortunately. So this is the goal of our research. So there are 3 sub-goals here. We introduce a metric for estimating the suitability of a keyframe for inpainting a certain region of interest. We introduce an importance ranking of our criteria, and we demonstrate how to best balance evaluation matrix. We also demonstrate the impact of the proposed approach on real application cases. We address this problem by defining and formulating heuristics in diminished reality keyframe selection, which I give you some more details in a minute. We calculate the best balancing weights for those heuristics. Our method is on the basis of the state-of-the-art diminished reality in-painting method for generic 3D scenes in Paint Fusion, which is also from a group. To this end, we define several areas in the camera field of view in color and depth space. That includes region of interest and its surrounding regions and so on. I am not getting into the details, but I try to cover the context due to the limited time. For the details, please refer to our paper. Please note that we focus on a single keyframe in painting in this research because it's the minimal requirement and thus the most applications do so. Let's put this aside. So there are 6 rules, starting from rule 1. Keep region of interest fully inside. In painting, algorithms find pixels from the surroundings area to fill in the region of interest. I will always show good and bad keyframe examples here on the right for an easy comparison by visual. Without surrounding pixels, it is hard to connect smoothly the boundary to the other, or it needs to continue the in-painting of the first keyframe in the next frames or in additional keyframes, which requires some efforts to keep consistency over the frames. To complete a keyframe in-painting fully, we do not use a frame when the region of interest touches the boundary. Simply, we count pixels of region of interest that overlaps the boundary pixels. Rule 2. Secure source areas. When more pixel resources are given, it is easier to in-paint a region of interest. More pixel variations can omit noticeable repetition in the in-painted area. The best practice for this issue is to simply keep the distance from the target object in practice, but the system should tell that to the user. We measure how many pixels occupy in the field of view. Rule 3. Secure similar pixel resources. For better pixel connectivity, the system should guarantee that the scene contains similar colors in the near surrounding pixels and those in the far areas. In these bad examples, most of the region of interest touches the green carpet, but some parts touch the toy train. Then the majority wins and the connection around the toy train part breaks. We calculate histogram correlations between the near and the far areas in color and normal maps. Rule 4. Minimize perspective distortion. Perspective distortion can easily break the in-painting since far pixels that show the same object smaller might be used to closer areas. This rule applies to systems that assume planar or near planar scenes. Therefore, in 3D in-painting systems, it might counterintuitively work, but or it actually does, as I will show you in our experimental results later. One may warp the image so that planes are rectified. However, this applies only to near plane scenes. We evaluate how many normal vectors face towards the camera backwards direction. Rule 5. Avoid depth discontinuity. The more occlusions will introduce more problems because depth in painting often assumes smooth geometric connections. We count depth discontinuity so that we can select our frame with less depth discontinuity. Finally, Rule 6. Reconstruct the scene fully. 3D in-painting relies on depth samples from the system. That is, the scene should contain enough number of depth pixels. Since users do not see the reconstruction running in the background, especially in applications showing the visible color space. Therefore, the system must internally know how many reconstructed pixels exist within the field of view. Now we have defined 5 rules, or the metrics, and somehow we need to balance them to get the final metric score or value. To do this, we assume a linear combination of the criteria. Thus, our goal here is to calculate the weight, WK. To do this, we minimize the difference between the calculated score and our balanced score, and to find the weights. We use LPIPs to evaluate the plausibility of in-paint results. We create our own dataset to collect keyframes with variance in our measures and to avoid pathological examples. For the final weight, we average the scores of color and depth, but here let me show you the individual results. As a short summary, the rules for the size of regions of interest and depth continuity have higher impact. The other rules with subtle weights have subtle weights, and this suggests difficulties of a keyframe selection, especially when the two major rules do not show differences over frames. For example, when the user keeps distance from the target object and the background depth is smooth enough. As I quickly explained before, the rule for normal directions has a negative impact in our 3D scene dataset. We conducted two experiments to evaluate our weights and the other two baseline approaches. First, we compare ours, WS here, with average weights approach, AS. Namely, we set uniform weights to our system. We evaluate the probability of how likely ours selects better keyframes than the average weight approach does as their best keyframes. Similarly, we evaluated the worst keyframes. We also evaluated ranking ability, which tells us how likely LPIP scores of AS and WS on their best keyframes are lower than those of their worst keyframes. The graphs on the right shows if the bar goes above the 50% or not, and ours is better than the average weight approach. In the second experiment, we compared our method with the averaged weight approach and random selections. Random selection means to randomly select frames in a video and check the quality of the in-painting as a novice user would do. Again, we evaluate the probability in videos with different lengths. The results show ours is over 50% probability in average. We also discuss standard deviations in a keyframe to show the stability of in-painting results from random sheets, but please refer to our paper for the details. We implemented 3 applications to demonstrate how people can apply our approach to their diminished reality systems. The first example is automatic keyframe selection, where the system can automatically select the best keyframe from previous frames. The second example is user navigation to guide the user to let them seek a better keyframe instead of selecting the best keyframe from the previous recorded frames. The third example is marker hiding, which is a popular application in diminished reality to virtually implement markerless tracking with a fiducial marker. In this case, we only apply 3 criteria. So this slide shows our contributions again and limitations and future work. Thank you for your attention.
Thank you very much. We're glad to see that the presenter is available to take your questions. So we have time for one quick question. Yes?
Thank you for the talk. So you used the LPIPS measure on the inverse depth, right? Usually LPIPS is applied only on RGB frames. Is there any work on applying LPIPS on inverse depth, or did you conduct any experiments to verify the validity of that?
So the intention of the use of LPIPS is to simply measure the plausibility of the depth maps. So maybe it's difficult to grasp the idea behind it at a glance. But the in-painting just simply in-paints some hallucinated pixels. So that means that we cannot. It is kind of meaningless to measure directly, for example, the inverse depth map by using RMSE or something like that. So yeah, that's why we use the LBIPs.
Okay, thank you.
Thank you very much. So let's thank the speaker again.
Thanks.
So the next talk is titled Instant Automatic Emptying of Panoramic Indoor Scenes. It sounds like decluttering of indoor scenes. We could all use that. The authors, this is a TVCG paper, so it was submitted to ISMAR's journal track. It's an IEEE TVCG paper. And the authors are Giovanni Pintore, Marco Agus, Eva Almanza, and Enrico Gobetti. And it's an online talk, an online presentation as well.
Hello everybody. Would you like to introduce our work about instant and automatic emptying of an indoor panoramic scene to support VR applications? Given a 360 panoramic photo of a cluttered indoor scene, our approach automatically returns a photorealistic view and depth of same scene emptied of furniture and clutter. Both visual appearance and depth, estimated at interactive speed, are highly suitable for compelling and immersive XR applications, such as refurnishing or for planning of interior spaces. Omnidirectional imagery is becoming a fundamental component for creating immersive content from real-world scenes and for supporting a variety of virtual reality applications. Furthermore, virtual tours based on spherical images are extremely popular in the real estate domain, and have rapidly increased their appeal in the pandemic period. Prominent examples include the emptying of rooms before their presentation to virtual visitors, or the refurnishing or redecorating of interior spaces. In this context, fast and effective diminished reality techniques, which conceal real-life parts from the view field, are paramount to remove the furniture and other clutter that masks the architectural structure. In particular, DER features are essential to allow users to immediately compare the furnished and unfurnished scene, and to support augmented reality applications in placing objects in the empty scene. Data-driven solutions are emerging as viable approaches for diminished reality. However, state-of-the-art methods are mostly focused on photorealism, and additional information about the scene is exploited only from the semantic point of view. Current pipelines make limited use of the structure of the observed scene, and reconstruction accuracy is achieved at the price of high computational complexity or increased user intervention, using, for example, recursive networks, multi-branch architectures, and manual definition of specific parts of the original image to be removed. In this work, we present a novel lightweight end-to-end deep network that, from an input 360 image of a furnished indoor space automatically returns, with very low latency, an omnidirectional photorealistic view and architecturally plausible depth of the same scene emptied of all clutter. It should be noted that our model is trained on structured 3D synthetic datasets, but we obtain state-of-the-art results even on real-world capture scene, thus demonstrating our transfer learning capabilities. We summarize here our main contributions. We propose a lightweight end-to-end deep learning technique, which develops in a linear fashion, with no need to fuse features from parallel branches, or to refine the result recursively. In order to alleviate the burden of convolutional gating for generic user-assisted in-painting, we adopt instead a depth-separable gated convolution strategy, and both visual and geometric constraints are applied only at training time. We predict a geometric representation paired with the output image, that is a dense depth estimation of the empty scene. This geometric representation can be directly used as a basis for further processing in XR application. We also exploit it to define a robust and effective pixel-wise prior together with other 3D priors and losses. We drive our training using a loss function that combines photorealistic and geometric terms. In particular, our geometric terms exploit both pixel-wise information and high-order constraints typical of man-made indoor structures. Here the scheme of our solution. We process the input equirectangular image to identify the cluttered area in the scene, exploiting, as first step, a pre-trained light-await network. The clutter mask and the input image are passed to the empty scene synthesis network, whose last layer is split in two layers, one for the photorealistic equirectangular representation of the emptied scene and one for its depth. The first stage of our method consists of an identification of the area containing the clutter that should be removed from the image to generate the empty room color and depth panoramas. This identification consists of a binary mask, where, contrary to many current DR approaches, that are oriented to the removal of single objects, we do not expect that users define it interactively. We define as clutter the portions of the environment that have an appreciable geometric volume in the room, but are not part of the bounding architectural structure of the room. Flat objects such as electric outlets or decorations, or mirror images, thus appear in the empty room by design. We adopt a very lightweight encoder-decoder network based on the U-net, trained by a binary cross-entropy loss. We adopt an encoder-decoder scheme which follows a common design for image in-painting. Compared to the standard baseline, our architecture is thinner, deeper, and with fewer parameters. In order to simplify training and guarantee low latency at inference time, our network uses a modified version of gated convolutions called lightweight gated convolutions, LWGC, which reduces the number of parameters and processing time while maintaining the effectiveness. Our loss functions are designed to combine a visual term that measures the photorealistic quality of the output with a geometric term that drives the solution towards a plausible reconstruction of an indoor environment. The visual term uses typical in-painting losses. The geometric term is a combination of low and high-order 3D constraints. The low-order term is a robust depth pixel-wise loss. The high-order term, based on the concept of virtual normal, is a high-order 3D geometric constraint, preserving the global shape of the model. Such an approach is very effective for indoor environments, typical composed of the union of a small set of smooth surfaces. We use structured 3D to train, validate and numerically compare our results to ground truth and other works. Then we test it on a large variety of indoor scenes, from publicly available datasets, such as Matterport 3D, and on scenes captured by non-professional users. Our method is clearly the most lightweight and scalable and has a lower computational complexity than the compared in-painting methods. We present some examples of our qualitative performance, compared to structured 3D ground truth and to other methods. We choose to compare our approach with Bono DR, since it was specifically designed for a diminished reality on panoramic images and, in our tests, it is the best performing among the other tested methods. Our method performs well under different conditions, such as near and far objects, poorly or highly textured walls, more or less distorted foreground, as well as background occlusions. We also shows the depth produced by our method, which is not computed by the other in-painting solutions. We compared our performance to several state-of-the-art in-painting methods, which are representative of the most related approaches. To provide a quantitative evaluation with respect to ground truth, we train all methods using structured 3D. Our method outperforms the other approaches on all considered metrics. Although our method is focused on the photorealism of the scene and not in-depth estimation itself, to provide a term of comparison, we compared our method with state-of-the-art publicly available networks for panoramic depth prediction. We present qualitative performance on data for which no ground truth or training set was available. This situation is the expected usage of our method. In all cases, our method is able to predict compelling empty scenes on real data acquired with different devices, automatically removing various types of clutter and very heterogeneous furniture. Here we show the contribution and performance of the different solutions proposed by our method. Our model proves versatile on different types of indoor scenes, even as the type of real or synthetic input data varies. However, there are cases, mainly in real-world scenes very different from training data, where our method did not produce plausible images. As an example, the particular conditions of illumination and the presence of many reflections do not lead to a plausible reconstruction. We have presented a new data-driven approach that, from an input 360 image of a furnished and cluttered indoor space automatically returns, at interactive speed, a 360 photorealistic view and depth of the same scene emptied of all furniture and other clutter. The accuracy and speed achieved could make it possible to consider immersive dynamic scenarios with acquisition and modification of the scene, even in motion and in real time. In the future, we plan to extend our work in this sense, also considering the lighting model and the spatial coherence of prediction. Thank you for your attention. For more information, please contact us.
Thank you, Giovanni. Can you hear us? Thank you very much for the talk. Okay, there you go. So we have time for one or two quick questions. Anyone from the audience? So I will say that we had a harder time following the automatic narration, so we would have loved to hear you do it, but anyway, that's for future reference. So I have a quick question. Do you think that emptying of the indoor environment should be connected to replacing what was inside with new furniture? And is this a necessary step, or can you directly simply replace or rearrange the furniture as other work has done?
Yes, exactly. That's a good point. Especially in our work, we are focused not only on the appearance of the empty environment, but also on the geometry. Why? Because I think also the geometry in the background is also easy to perform, refine here, to move objects, to inside new objects, or also to synthesize, for example, squatting, obtaining new views. So basically, it's an enabling technology in order to support novel application, VR, XR, exactly like this. We focus our attention not only on the visual and perceptive parts.
Thank you. So if there are no other questions, let's thank the speaker again. So we're moving on to the last, but definitely not least, the talk of the session. So this is a ISMAR conference paper, and it's going to be presented in person. As you can see, the speaker is getting ready. So it's a portal rendering and creation interactions in virtual reality. The authors are Daniel Ablett, and he's the speaker, as well as Andrew Cunningham, Gan Lee, and Bruce Thomas. So Daniel, please go ahead.
All right, thank you. My name is Daniel Ablett, and I'm a PhD student at the University of South Australia. I'm here to present our paper, Portal Rendering and Creation Interactions in Virtual Reality. As said before, my co-authors are Dr. Andrew Cunningham, Dr. Gan Lee, and Professor Bruce Thomas. Portals are a novel technique for supporting visualizations and interactions between locations that are not co-located, especially in virtual reality. They consist of two sides, which we will refer to as the local and destination side. The local side is within arm's reach, and the destination side is out of arm's reach. In our paper, we investigate both rendering portals in VR and the interactions to create these portals. We devised our portal rendering solution from existing rendering elements and called it Infinite Single-Pass Stereo Stencil Multi-Portal Rendering. While it's a bit of a mouthful, it was named so to identify the unique combination of rendering elements that define it. Our paper describes our algorithm we propose, but here I'll just describe the key elements. As VR trends towards standalone mobile devices, it was important that our algorithm be designed to run performant on those mobile devices. It should be noted here that the video is not recorded on a mobile device, though. There are two common approaches to rendering portals. Rendering to a texture, which is simpler but less performant, and then there's the more optimized approach that we took using the stencil buffer. Pairing this with single-pass stereo rendering, meaning both eyes share the same culling process and are rendered together, we were able to keep our algorithm high-performing. As shown in this video, our rendering solution supports any number of portals. It also supports infinite recursion of these multiple portals. Our rendering technique was guided by a concept first introduced in Valve's game Portal. The developers of Portal have previously discussed their process of rendering portals and given details about their solution for mimicking rendering of infinite portal recursion. Behind the scenes, they would reuse the render from the previous frame and shrink it down inside their portals. As each frame is rendered, this adds an infinite effect with minimal overhead. Our approach goes a step further by adding stereo and allowing for multiple sets of portals to appear infinite. By recognizing repeating patterns of different pairs of portals, any of these complex sets have the same potential to be fake rendered. Finally, and arguably most importantly, we made our rendering algorithm open source. Our Unity implementation, built using the universal render pipeline, is available on GitHub. There'll be another link available at the end of the presentation. We benchmarked the performance of our rendering algorithm against various portal rendering alternatives, the implementations of which were also created using Unity's universal render pipeline and are available on the GitHub. We recorded the performance natively on a Meta Quest 2. The Quest 2 was chosen because of its current popularity in the VR market. We compared our algorithm against alternatives with multi-pass stencil portals, single-pass render texture portals, and multi-pass render texture portals. 4 sets of portals were created for the benchmarking. Each set was tested for 0 to 40 portal renders with and without shadows. This resulted in a total of 320 conditions, where each was tested for 15 seconds. Then the average frame rate and texture memory were then calculated. Here you can see the frame rate mapped against the number of portal renders. Our algorithm is the highlighted blue line inside the single pass stereo box at the bottom. Without shadows, our algorithm performed with the highest frame rate, followed by multi-pass stencil portals. Both the render texture portals performed the worst. Our algorithm consistently used the least amount of texture memory. For one set of portals, the texture memory usage flattens out for all variations. But as the number of portal sets increases, the memory usage of render texture portals escalates considerably against the number of renders. This is not the case for stencil portals, as their texture memory remains constant, independent of the number of portals or recursions. Now I'm going to talk a bit about the portal creation interactions. I'd like to quickly give some background into related portal interactions in VR that guided our work. Liu et al.'s redirected teleportation technique allowed users to create portals using a curved ray, something common for teleportation interactions in VR. This technique allowed users to select on the ground where they wanted a grounded portal to appear. Tunnel windows was a VR interface by Kurikawa et al. Portals could be created using a pinching and dragging motion. Both sides of the portal began on top of one another, and one side would then need to be moved by grabbing the frame. Kerner et al. Used the metaphor of photography for their VR portals that they referred to as photo portals. Photo portals use a capture metaphor both to create and adjust portals. They moved together until capturing was released. The destination side then became static and no longer moved to the local side. This allowed photo portals to be moved freely while keeping the destination sides unchanged. This, with tunnel windows, would be the basis of our locked and unlocked interaction. While placing the local side of a portal is simple, placing the destination side in a meaningful way is not. Dr. Strange may be able to create a portal wherever he wants it, but we don't have the luxury of magic. In our paper, we developed 4 handheld creation interactions to make creating portals quick and easy. The baseline that we used to compare our interactions against was the most basic creation technique, simply creating the portal so that both sides appear in the user's hand. This approximates the creation techniques used by tunnel windows and photo portals. As the technique does not do anything to select the placement of the portal, we added standard controls to allow the portal to be moved from its starting position. Portals could be steered around using a joystick, as one would do in a first-person game. These standard controls also included locking and unlocking, which was similar to the capture concept in photo portals. These standard controls were not exclusive to the baseline, as all techniques could use them for adjusting their initial placement. Our fishing reel creation technique was inspired by Bowman and Hodge's fishing reel object manipulation tool. When the portal is created, the user can reel the destination side outwards. This technique was designed to be performed while looking through the portal, appearing visually like a magnifying glass. For this reason, it does not support axial rotation of the destination side, as the perspective quickly becomes confusing. Our raycast with reel creation technique is an extension of our fishing reel technique. It adds an earlier step where the initial length of the fishing reel's rod can be set to match a raycast. In theory, this makes raycast a faster version of the fishing reel interaction. Our marker creation technique works by giving the user an abstract representation of the portal to interact with. Like with fishing reel, the marker can be pushed outwards, but it can also be rotated. Once the user is satisfied, the portal destination side is created, replacing the marker object. The marker is visualized using a 3D gizmo where the blue line represents the direction the portal will face. Like redirected teleportation, our projectile curve creation technique was inspired by point and teleport. First, the user projects a curve to show a cursor on the ground. We then added the option to direct this cursor using the joystick. When the user releases the curve, the portal appears with the local side in their hand and the destination side positioned at a matching height and angle above the cursor. We conducted a within-participant user study to evaluate our 4 creation interactions and compare them to the baseline. 25 participants were recruited, 5 females and 20 males, with an age range between 18 and 42. All participants were required to have normal or corrected to normal vision. Participants were first given a tutorial to introduce them to VR, portals, and the standard controls for using portals. They were then provided with training for each creation technique with an example of the trial. As the actual task for these trials, participants were placed in a virtual environment with a 3D model in the center. They were given a reference portal, shown here with the green frame, that they needed to replicate. This required using the given creation technique to create the portal, as well as using the standard controls to adjust and finally place the portal. Participants press the green button at the bottom of their portal to finalize their attempt and move on to the next. This is repeated 10 times for each creation technique with varying reference portals to cover all of our conditions. There were 2 variables we used to place our reference portals: distance and direction. Distances were close or far, and directions could be front, front side, side, back side, or back. Linear mixed model analysis was used to analyze the results of our study. The models were specified with 3 fixed effects: technique, distance, and direction. Type 2 walled chi-square tests were used to test for significance with a threshold of 0.05. Based on our analysis, we found that projectile curve was the overall best technique, which I'll justify here. For placement time, defined as the time it took for the participant to create the portal using the technique and adjust the placement using the standard controls, we found a significant ranking where projectile curve and the baseline performed faster than the other techniques. We also analyzed specifically where the time was spent, split between technique time, defined as the time that the technique was actually in use, and correction time, defined as the time to adjust the initial placement using the standard controls. As the baseline interaction instantly places the portal with no thought to its placement, it could not be meaningfully divided into these 2 sets and was excluded. We found a significant rank order for technique time where projectile curve and fishing reel were the fastest, followed by raycast and then marker. As for correction time, we found that projectile curve required significantly less correction time than the other 3 techniques. We found significance for multiple interactions in relation to technique error, but of interest here is technique against distance. In the close cases, as in those where the reference portal was close to the model in the center, the projectile curve had significantly more error than marker and fishing reel. This is of interest because even though it had this high initial error in the close condition, projectile curve still maintained the fastest correction time out of all the techniques, as you saw in the previous slide. Analysis of participants' preference showed projectile curve and marker to be ranked the highest. As the projectile curve outperformed marker in most measures, we reason that projectile curve is still the better of the 2 and the overall best technique. To reiterate the contributions of our work, we presented our portal rendering algorithm, we benchmarked its performance, we presented our 4 handheld portal creation interactions, we evaluated those techniques in a user study, and I'd finally like to end by bringing focus back onto our open source VR portal toolkit. There are several different ways to create portals, and we've implemented many of them that you can use for free. Portal rendering is difficult, especially in virtual reality, to do it in an optimized way. So we'd love to encourage more research into portals and non-Euclidean space in virtual reality. So we highly recommend, encourage researchers and developers to give our toolkit a try. Thank you so much for listening.
Thank you. Questions from the audience? Yes, a question at the back.
Thank you for the nice presentation. So I had a specific question, especially with respect to the marker versus the raycast approach.
Yep.
So in the marker, you had this 2D perspective of a marker which could be moved by the user.
Yep.
And you said that the correction time was more or less comparable in terms of when the correction times were compared, when you used the marker versus the raycast, the results were more or less comparable. Was the projective view, the 2D view, also influencing in terms of making an error when using the marker?
I'm sorry, could you say that last part again?
Sorry?
Sorry, could you say the last part again?
Yeah, so when you, since it was, a marker was like a 2D view, was there any bias in terms of deciding the 3D position when using a marker?
So because the marker wasn't a 2D thing, like it was a 3D shape with a like a gizmo.
Okay, so it's
around.
it was a 3D marker.
Yeah, it was a 3D marker.
And okay, so 3D marker was able to also have a 3D position information. Yeah. Okay, and that also was helpful in making a decision.
Yeah.
Okay, then I'm sorry, I think I got the point
worries.
right. Thank you.
Any other questions? So one last quick question. Can you tell us about future work thoughts? Is this something that you could use for teleportation, for example, or for what other non-Euclidean navigations or renderings of the virtual reality space?
So moving forward, because with projectile curve being an obvious winner in this, developing further on that so the projectile curve is a much more natural technique, also allowing for projectile curve to be repeated after creation is something we're working on at the moment, because going around corners is like any creation technique. Anything out of line of sight is slower, but you want to be able to make sure that people can create portals that are convenient for different locations that you might not be able to access on foot. So by being able to repeat the projectile curve process over and over, you can get to anywhere. And so that's kind of where we want to then look at interactions you can do through portals that you've set up that way.
Sounds great. Thank you very much. So let's thank the speaker, and let's thank all the speakers of the session. This was the last talk of the session, so thank you very much.